In today's Retro Tech Repair, we're going to be trying to fix this Gakken Puck Monster that I bought spares or repair on eBay.
So here we have our Gakken Puck Monster. Looks to be in fairly good cosmetic condition. I think it's sold in the UK under the brand Computer Games Limited, but was made by Gakken. In fact, Gakken is a company I think that's still in business. I've seen some things from Techmoan on his channel that came from Gakken, but I don't know if they're making electronic games anymore, more educational kits and toys, I think. Anyway, whether that's true or not, here's our Gakken Puck Monster. Let's take a look at the eBay listing for this one. So I don't have the original listing because I bought this back in August of 2020, but here's a summary. Vintage CGL Puck Monster LCD handheld game, repair or. I paid £11.50 plus £3.10 shipping, so a total of £14.60. So there's sound but nothing on the display. Let's see if the game's playing. I think it is. Yeah. I think the game is playing, but we can't see anything. There's nothing on the display. We still have sound. So the processor's running, but the display isn't working. Let's take a look inside.
So I remove the batteries and then 4 screws hold the top enclosure to the bottom enclosure. A further 4 screws hold the printed circuit assembly in place, and with those removed I can gently lift the printed circuit assembly to the side and slide out the connector for the power supply. Game sound comes courtesy of a piezoelectric sounder that has a plastic cone attached to it via a locking ring. With the locking ring removed I can lift the cone away, and then all I need to do is unsolder the wires from the battery terminals to give me unfettered access to the printed circuit assembly itself. So we're going to take a similar approach to that which we've taken on other videos. We're going to start out with a visual inspection, and then we're going to look at power, connections, transistors, diodes, and then finally capacitors and resistors. And if we find something that piques our interest along the way, we'll probably divert and take a look at that too. For the visual inspection I'd usually use a loop magnifier, but I've got a new toy which will enable me to share some of what I might see, so let's go ahead and try that. So ordinarily I'd be doing this just with a magnifier, but on the component side of the board, what I'm looking for are any burnt or damaged parts, anything like that, and I'm not seeing anything here that looks particularly suspicious at all. So we'll move on to the other side of the board. On this side I'm looking a little bit more closely, and I'm going to look at all of the solder joints that I can see, and I'm going to look at all of the tracks. And I'm going to spend probably about 15 minutes doing this. If I see anything that's suspicious, I'll take a closer look at it. So there's something here that looks a little bit suspicious, but it looks like it's made contact anyway. And then I will continue through the rest of the board. Again, something looks a bit suspicious there, so we'll take a closer look at that. I think that's actually just the joystick pad, and when I look at the joystick connections, each of those seem a little bit dodgy, but I don't think they are going to be the cause of the problem. Alright, so having passed the visual inspection, we're now going to move on to power. I have my bench power supply set up off camera here, and we're going to hook that up to the wires. I think we need to remember the polarity. It was positive to this one, negative to this one, and we're going to have the power supply set to about 6 volts, which is what we'd expect to get from the 4 C cells there. Okay, and let's switch it on. Just keeping an eye on the current. And that current is way too high and the voltage is dropping. That's not good. I think we're probably going to see some heating soon. Transistor D882 is getting pretty warm. Ow, but that's getting super hot now. Yeah, that shouldn't be nearly an amp. It should be maybe a quarter of that, even less. So we have a problem with this board drawing too much current. I'm not going to try and chase that 5 volts around. I'm going to take a diversion and try and figure out more analytically perhaps what's going on with this overheating here and the big current draw that we're seeing.
So you'll know if you see my videos before that usually I'd start systematically testing components on the board, just one after the next, until I got through them all, because these are fairly simple boards and it's fairly quick and easy to do that. But I've decided, since I've repaired so many of these games now, I should take a little bit more time to understand just how they work. So that's what I'm going to try and do. So I did a little bit of research online, and it turns out this microcontroller here requires a 10 volt supply, or about a 10 volt supply. The display being a vacuum fluorescent display, I again googled a bit on these, and they need, I think for the filament voltage, probably 2 or 3 volts, and then for the anode and cathode, because they are kind of a vacuum tube, they emit electrons from one side, and that excites a phosphor that's kind of built in there. So I think they take maybe 15 to 50 volts. I'm thinking probably about 30. So how do we get those voltages from our 6 volt supply? After all, this game, when it's configured and working, takes 4 C cells. So I think the key is this little fella here. This is a transformer. It's anonymous, it's not marked, but if you look carefully inside of it, you can see that there are some kind of wires looped around ferrite cores in there.
So my theory at this stage, which could be entirely wrong, is that this is a multi-tap transformer which is used to generate the various voltages needed by the components of the board.
So this would be your input, this would be your output, and then there's kind of a ferrite core down the middle. So they're not electrically connected, they're magnetically coupled. And what that means is that if you put an alternating signal in this side, then you get alternating signals of different voltages out of the other side, and the ratio between the number of turns here and the number of turns here gives you different voltages. And I think that's what's going on with this transformer. So then I thought, well, I'm going to take my multimeter and start buzzing this out, or measuring resistance on it. And what I've discovered is, starting from the transistor here, the D882 transistor, it looks like there is one kind of coil here. When I go on there, it connects to one other with a small resistance, as you can see. I see that 2 of these pins are connected to each other, but then they are not in turn connected to any of the other pins on that transformer. Now when I move on to the next one, that is connected to one, and then another, and then another. So it looks like that's got 3 taps on one coil.
And I continue to measure the transformer, and it looks like there is another coil that has 4 taps.
So I think we have one kind of set of coils which has just 2 taps on it, and then a 1, 2, 3 tap, and a 1, 2, 3, 4 tap on this little transformer here. So you remember from our drawing of the transformer that I said this needed to be an AC voltage in order to get these AC voltages out here. So I think probably what's happening when we look at our circuit is that these diodes are converting the output AC voltage back into kind of DC. They're maybe doing some kind of rectifier function, something like that, in order to drive the microprocessor and maybe the display, or maybe the display is taking AC, I don't know. But then these transistors are trying to take that DC voltage, that 6 volts, and turn it into an AC voltage that can then drive this transformer. So in a sense, they're an oscillator. So I've pulled the data sheet for the D882 and for this microprocessor, and also for the other transistor on there, which is a C945. So I think what I'm going to try and do now, using the data sheets, and I have a couple up on my computer as well, and just looking at the board here to see where the tracks go, how they connect this transformer to these components here, what these diodes do, maybe where the power supplies are. I'm going to try and backwards engineer this, I suppose, draw a circuit diagram for the bits that are on the low voltage side of this transformer, in the hope that I can see how those would be working and understand a bit more about it myself, and maybe that will help us diagnose the problem without having to systematically go through testing all of the parts. And even if I'm unsuccessful, then hopefully I'll learn a little bit about how this works and how the other VFD games that I've repaired in the past have worked, and that might help me repair more games in the future. So I'm kind of excited to do this.
So just as I described, I tried to draw the low voltage side of the transformer, taking consideration of the pinouts from the transistor datasheets and the connections that I see on the printed circuit assembly. Please don't take any notice of the diagram that comes out as a result of this, because it's almost certainly wrong.
So that took me quite a while, perhaps more than I even showed on camera, but when I look at this configuration here, and I googled oscillators, I think what I've drawn is something called a relaxation oscillator or maybe a blocking oscillator. And I think what could be happening here, or maybe should be happening here, is that these two transistors are, or this transistor is kind of oscillating here and controlling the base of this transistor. And then this transistor should be turning on and off to generate the kind of AC signal here, which then goes into the transformer, and then on the other side of that we generate all of the voltages for the VFD display and so on. If this transistor is stuck on, so it's conducting all the time, then essentially it's going to have more or less a straight route through to the 6 volts down to 0 volts. So what I'm going to look at now is this D882 is often the cause of failure, but when it is the cause of failure, I've nearly always seen a short on that, and I'm not sure that that is still the case. So I'm going to start by taking the C945 out of circuit and checking that in my component tester. If that doesn't work, then I'll go on to the D882, and if it's neither of those, then perhaps this diode circuitry over here. But these are unmarked, so it's going to be quite hard for me to work out what those are. Please do not take this circuit diagram schematic to be an accurate representation. It probably isn't. I've probably made some mistakes. I'm not very good at this, and actually I don't enjoy this particular part of it that much, but I really have enjoyed understanding more about how this circuit works. So it's going to be very exciting for me to see if this C945 is actually the cause of the problem. There we are. Moment of truth. I'm just guessing this isn't going to be the problem now, but it's been fun. Slide this in here. I've had a few questions about this component tester. I got it on Amazon. You can get them on eBay also. They're very, very cheap and really quite useful. Let's see how it does. Oh, and it recognizes it straight away as being an NPN transistor. So I don't think this is the problem. Oh, what a shame. Well, I'll leave it out for the time being, and we'll check the other transistor, the D882. And it's recognized that as an NPN transistor too. So something must be turning on this transistor to turn on this transistor all the time, and for some reason this isn't oscillating, and I don't know why. So everyone loves to blame capacitors, don't they? So maybe that's the problem. Well, the ESR is nice and low, and it's measuring 13 microfarads and it's rated at 10, so that's about right. So I did remove the diodes, these two here, which are these two here on the board, and I tried them in the component tester and they test fine as well. So now I'm going to move on to the next suspect diode, which is this one here, which in this orientation shows 1.4 volts voltage drop, and in that one shows 0.6. I think it's good, but I'm going to try take it out and test it out of circuit anyway. Well, haha! That does look suspicious. The only problem is that I can't see any markings on it, so I don't know what that part is.
So there are no markings at all on the diode, and when I put it in the circuit tester, it shows as an unknown or faulty part, which is good news, I suppose. We just need to find a replacement.
And when we connect it up to the bench power supply with that part removed and switch it on, the current draw is much more like we would expect it to be, less than 1/10 of an amp, and although it still isn't working well, we wouldn't expect it to work with parts missing, this transistor is no longer running hot. So whatever that part is, I'm starting to be convinced that that is part of the problem. So of course we have a slight problem because we can't tell what our mystery part is. It's unmarked, it's just a diode with a blue line on it. Sometimes the blue line means a Zener diode, sometimes I think it doesn't. So I have no idea what value that is. So what I'm going to try and do is I'm going to solder some little jumpers into the board just where that diode was, and then we can try different components in there and we can see if we can find something that will make this work. So just for fun, I drew the mystery part onto the circuit diagram, and it's just here. It's on the second half of the transformer, and it connects to a pin on the processor called V-display. Looking at the datasheet, V-display is the voltage or supply for the display that goes into the microprocessor, and then presumably the microprocessor then drives the display from that. That voltage is a maximum of 50 volts. So I'm going to start off by putting the highest value Zener diode in, which I have, which I think is around 22 volts. Okay, so I have a couple of clip leads now attached to the wires that I'd soldered in the board, and I've got a selection of diodes that I'm going to try and see if we can find one that makes the game work. So I'm going to start off with a Zener diode. This is from a little kit that I had, and a highest value in there is 22 volts, Zener or Zener if you prefer, and that's the first one I'm going to try. So we'll clip that into circuit now, and we're also going to keep an eye on the current drain to see how that does, if we get one that works. Oh no. No, that doesn't work at all. In fact, it kind of shuts down. I'm sure I've got that the right way around. I think I have. Yeah, no, that's not good. So the 22 volt Zener is not the answer. So this is the next one that I'm going to try. It's a 140 volt Zener, or Zener diode if you prefer, that I've used in the Astro Wars repair that I did in my Astro Wars repair special a little while ago. They're no longer manufactured, so they're a bit harder to get hold of. Alternative 140 volt Zeners are available, but it'd be nice to be able to find a part that we can use that's perhaps more common. Let's try this one and see if it works. Aha! Hey! Oh, that's great. So it looks like we have a solution that would work. Looking at the amperage it's drawing, about 1/4 of an amp. I think that's about right. That's about what I would expect. The flickering that you might be seeing on the screen now is just the way I have the camera set up. It's not evident in front of me. So this is a little warm. This Zener diode is a potential replacement. So the next diode that we're going to try is one from a scrap board. This is a Firefox F7. Obviously it's not a Puck Monster board, but there is a diode here in a similar kind of position between the output of the transformer and the processor, although both the transformer and the processor are different. But that's S11, so we'll pop that out and we'll try that as well, see if that will work. So here we have our salvage diode. Let's try that. Nope, it's a lot of current draw, but no action. So that, whatever it is not a contender. We'll pop that back where it came from. So up next then is our Diode Assortment. 10 values, 200 pieces, so you can focus on that. There are probably some people watching who would know which one to install, but I don't, so I'm just going to select some. And I'm going to start with the highest number, and then we'll try the lowest, and then maybe we'll try something in between. So let's start with this. I suppose I could look at the data sheets and see what the differences were, but this is a 1N5819, so let's try that. Aha, well, some success. The display's pretty dim though, it's in and out, and the current draw is really high, so that's probably getting hot. Yeah, it is. Okay, alright, so it's not one of those. Let's try the other end of the scale, assuming it is a scale, which is a 1N4001. And that looks much better. Display's pretty bright. Current draw is about what it was with the Zener. That's looking promising. I do hear just a little buzz from the piezo sounder. Not sure what that is. Doesn't seem to be running very hot. Although it looks like the current is maybe increasing slightly, certainly when I touch it, it does. As I say, the flashing that you might see on the screen is not visible in person, it's just the way the camera is. Yeah, but that's not bad. So that's a definite possible, the 1N4001. Let's just try one that's somewhere in the middle of the range here. This one is a 1N4005. It looks like it's got slightly meatier legs. And again, that seems to work just fine. In fact, the current draw, it's about the same as it was before. So yeah, looks like these regular diodes seem to work, at least some of them do, and I don't know which one I'm going to choose yet, but I think this is one of the ones I'm going to put back in the game. So I noticed as I was playing the game that some of the buttons are a bit kind of sticky and slow to respond, so I'm going to clean those with a little bit of IPA2. I've got a piece of paper behind there, I'm just going to kind of rub those back and forth. I could unsolder them, but I don't think it's necessary. I think this is just going to be adequate.
So now all that remains is to get everything cleaned up. I disassemble as much as I can, clean it with window cleaner and a toothbrush before polishing with a microfiber towel and reassembling. I remove any scuffs with a magic eraser, reassemble the piezo sounder and solder the battery contacts back into place. After that, it's just a case of replacing the screws that hold the printed circuit assembly in place, and then finally the 4 screws that hold the enclosure together.
So it looks like if we just followed the plan, not got too excited trying to draw circuit diagrams around power, we'd probably have quickly resolved connections, we'd have checked the 2 transistors, and before we knew it, we'd have been at diodes. So probably the analytical approach might not have been the best thing to do in this case. And I almost forgot to mention the part that I used was a 1N4005 diode.
So as a VFD implementation of a popular arcade game of the day, I think the Puck Monster does a pretty good job. The gameplay is much better than the Tommy Munchman that I repaired in the early days of the channel, and it's better than a number of implementations of Pac-Man that I remember from handhelds back in the day. It features some nice colourful graphics and a changing maze from one level to the next, which is also a nice feature. Anyway, that just about wraps it up for our Gakken Puck Monster today. I hope you've enjoyed the video, and that if you have, you'll consider hitting subscribe. But until next time, thank you so much for watching Retro Tech Repair.
Oops. And off we come with the lid.